Welcome back, ladies and gentlemen. In this video we're looking at forces, introduction to forces, in a very basic way, but we're going to hit some super important topics, concepts related to forces that you really cannot ignore. You can't afford to lose sight of these, even if we get into more detail later on. So why study forces? Well, objects interact through forces. Anytime one object interacts with another, it's through a force of some kind. And so whenever you are talking about a force, you're talking about two objects interacting with each other. That right there, right away, is a huge deal. A force is an interaction between two objects. So also, forces help explain why things happen the way that they do. Up till this point, looking at kinematics and the equations of motion and constant motion and accelerated motion and PT graphs and VT graphs and all the equations, that's just been trying to describe motion and represent the motion, but it has not attempted to explain the motion. Forces allow us to start to explain why. And that's really when physics begins to be very fascinating, for me anyway. When you start to be able to explain why and understand, well, why is it happening that way? That's so cool. So now, to get us going further, what is a force? Well, at its simplest, a force is a push or a pull. That's about it. It's a push or a pull. Forces cause accelerations. So remember this as well. Forces cause accelerations. This is so important. But what is an acceleration? If you recall, an acceleration is a rate of change of velocity. So if velocity is changing, then you could say, well, it's not constant motion, it's changing motion, it's accelerated motion. So you could also say that forces change motion, they cause accelerations, and that's really what happens. Now, before I go any further, let me explain something about this. Forces cause accelerations. Obviously, you can have an object sitting there. Got Mrs. Kangaroo. And so, are there forces acting on Mrs. Kangaroo right now? Well, of course there are. Earth's gravity is pulling down in the downward direction. The table is pushing back up. But we can clearly see that Mrs. Kangaroo is not accelerating, yet there are forces. So this is something actually that Aristotle and a few other people got wrong. And other people later on, particularly with people like Galileo and Isaac Newton, that they kind of came along and corrected the idea. We'll get into more detail of that later on. Don't worry about that for now. Just general idea, forces cause acceleration. Now, different kinds of forces. Two very broad categories that forces fall into, and if you remember these categories, it can be helpful, especially when you're trying to do some problem solving. There are what are called contact forces, and they require physical contact between two objects. And there are what are called field forces that do not require physical contact. The objects don't have to be touching. So contact forces, you could have an applied force. For example, someone pushing on a shopping cart, there's going to be you're applying a force to the shopping cart. The symbol we're using is a capital F. We've got this line over it like a half of an arrow, and we'll come back to that. This other thing called a normal force. Now, not normal in the sense that, well, it's normal, it happens all the time, kind of normal. Normal in a geometric sense, in that, well, normal actually means perpendicular. And think of normal force as a support force from a surface. The symbol we're going to use, capital F with a subscript capital N for normal force. There could be tension force. It's like a pulling through a rope or something like that. Capital F subscript T for tension. Friction force. Now we're going to study friction in some detail. It's one of the more interesting types of forces because there's quite a bit to know about it. And there's two general kinds of friction. There's static friction and kinetic friction. So we have F sub S and F sub K for static and kinetic friction. Drag force. So drag is basically like friction with the air. It's air resistance, F sub D for drag. Now, those are all contact forces. They require physical contact between two objects. Well, okay, right away you might think, well, wait a minute. If air resistance is a contact force, then what's the second object? As an airplane or a bird flies through the air, for example. Well, the second object are the air molecules bumping into and dragging across the surface of the wings and the body of the airplane, for example. Field forces. Field forces, remember, don't require physical contact, and yet they still represent an interaction between two objects. Easy. Gravitational force. Capital F sub G. Remember that little g relates to gravity. So gravitational force, you're very familiar with that. And if you think about this, now you're basically interacting with the Earth most of the time by being in contact with the Earth. But if you, say, are laying down in a bed, well, you're not touching the Earth. If you are sitting up on a stool where your feet are off the ground, you're not in contact with the Earth. If you jump up in the air, while you're in the air, you're not in contact with the Earth. And yet, Earth's gravitational force is still affecting you. So, it is a field force. Another kind of field force is electric force. We'll get to this later on. Capital F with a subscript lowercase e for electric force. These are not, by any stretch, all the possible kinds of forces that there are. There's just several examples. Just wanted to show you. Okay. So now, to wrap this up, how do we represent forces? What we do is we draw what's called a free body diagram. So here's the deal. Let's say you are standing on the Earth. You're just standing on the ground. And we're going to represent the forces acting on you while you stand there. So what we do first is we isolate the object we're concerned with. We're concerned with you. You're the object. And we're going to draw, not really like a graph, but we're going to draw you as a dot. We're going to replace you with a dot, and so we free you, that's the word free, we free your body, or the body of the object, from everything else. So that dot represents you in this free body diagram. Notice I have this label here. What are we representing? If without this label, it's kind of unclear. So this is a free body diagram of you. So clearly, and so here's what I'm going to do now. I'm going to draw arrows to represent the forces acting on this object. And the arrows will begin at the dot and all point away from the dot. Okay, that's important. But what are those forces acting on you? So I'm going to go through a checklist, so to speak. I'm going to ask myself, well, what are the contact forces? What's touching you? Well, the Earth is touching you. There's a contact force. So what could that be? Well, you might think applied force, but even better, normal force. You are supported by the Earth pushing straight up. And because this is horizontal ground, that force will be perpendicular to that surface, and that means that force is straight up. Now I've got these X and Y axes, and that really will help us, you'll see, sort of like a graph, but really just to represent, well, this is, we're calling this the Y direction, we're calling this the X direction. So we have a contact force, Earth is touching you. Nothing else is touching you in this situation, so no other contact forces. And so we have that upward normal force because of that contact. Earth's surface is supporting it. Now, how about field forces? So I asked myself, well, what's touching you? What are the contact forces? Now, what are the field forces acting on you? And clearly, Earth's gravity is pulling you downward. And if you're on our surface or near the surface, well, that won't really go away. There really aren't any electric forces that are worth considering, at least not right now. So it's just the gravitational force. And so we have these two forces acting on you, and they're both in the Y direction. Okay, and there are no forces in the X direction. There's nothing else touching you, and there's no big planet over on this side to pull you some direction. Now, one more thing, I drew these forces the same length as each other. And why do you suppose that is? I'll leave that to you for now. What you want to think about, though, is, well, what's happening in the situation as you stand there on Earth's surface? In this other example, so you are pushing a cart and you're both on Earth's surface. We're going to draw a free body diagram of the cart in this situation. So what's touching the cart? I'll go through contact forces first. Well, first we have, you're touching the cart, you are applying a force. You have an applied force. And since your push is that way, well, I drew a dot to represent the cart. I freed it up from the rest of the universe just by a dot. I have my X and Y axes on there. That contact force is in the X direction to push it horizontally. And so what else is touching the cart? Well, Earth is touching the cart. And the surface is horizontal. The force will be perpendicular to the surface. That means the force is vertical. I have that normal force holding the cart up. And one more thing, now there's a field force, Earth's gravity pulling down on the cart. Gravitational force pulling down. So I drew the gravitational force arrow, the normal force arrow, and the applied force arrow, all starting at the dot and pointing away from the dot. Good. Next, I drew the gravitational force arrow and the normal force arrow the same length as each other. Well, why did I do that? You go back to the situation and think about what's happening to the cart in the situation. But also, we have this applied force and nothing going the other way. Sort of nothing opposing that applied force. So what do you think is going to happen to the cart with nothing opposing, excuse me, nothing opposing this force? What would happen? I'll leave that to you for now. That's it for the basics of forces. Thank you for watching. I'll catch you next time.